Okay, so welcome back everybody, and today we are going to start a new chapter, which is the last chapter of Calculus 2. Chapter 10, the parametric equation and the polar coordinates. So we will first focus on everything about the parametric equation for 2 sections, and then polar coordinates is nothing but a special type of parametric equation. So if once you know everything about parametric equation, polar coordinates should be very easy to do. Okay. So the first thing we want to do is we want to talk about what is parametric curve. Curve defined by parametric equation. Okay. To see why we need this. So curve is something just like that, right? Before we have something called y equals fx. For example, y equals x squared is clearly a curve. It's a parabola. Now we want to represent it in a different way. And let's see where does the idea come from and why do we want to do it. Now let's consider a simple motion in physics. Okay. Here's 0, and you are at, let's say you're at the top of the building, which is 30 meters, okay, above the ground. And then at here, you horizontally toss up. You throw a thing horizontally, okay, with 0 degree angle of elevation, with, let's take 2 meters per second. So this thing is going to actually start from here and start to fall, and meanwhile travel to the right, and eventually it falls here. Then the motion stops. Good so far? Now, what we want to do is, we want to calculate what is the formula of this trajectory, because it's clearly a curve. And this thing should have a formula which is y equals fx. Maybe it's and as far as we know it's a parabola. Okay, so how do we do this? In physics, it's really difficult to calculate both things at the same time with the curve. So instead, what we do is we try to calculate two things separately. The horizontal motion and the vertical motion, because it's easier. Okay. And then the horizontal motion is given by the horizontal distance, okay, as a function of t, and the vertical is given by the same function of t with the different formulas. So together we use t as a time, and we calculate the horizontal trajectory and the vertical trajectory as a function of t. So for any points on this trajectory, this is going to be a function of t, and this is going to be a function of t. If we know both functions in terms of t, that means if we plug in time equals 2 seconds, 3 seconds, 4 seconds, we will know what both x and y are. Therefore, we know where the point is. If we know it's for all t, we know the whole trajectory. You know all the formulas of the trajectory. Okay? So that's a simple idea, and let's think about it. Here's the horizontal one, here's the vertical one. Let's think about force, or let's think about acceleration. Okay? Then let's think about velocity. And given these two, we will be able to find the trajectory. Okay, h, which is x, v, vertical, which is y. So horizontally, you don't have anything, right? There's no acceleration because there's no force, so 0 acceleration. Vertically, what do you have? Vertically, you have a constant acceleration, which is g, where g is the gravitational acceleration. That's why if you release something, hold it in the air and release, it will fall. And this g is roughly 10. It's 9.8 something. Let's just take it to be 10. Okay? Then what's the velocity? Well, horizontally, the velocity is going to be 2 meters per second, because initially you did a horizontal velocity and there's no force, no acceleration. Therefore, this one will keep traveling at the constant speed, which is 2 meters per second. What about the velocity vertically? Well, for a straight line motion with a constant acceleration, it's simply the acceleration times the time. Finally, what is the trajectory at time t? Then it's velocity times the time of t. That is my horizontal trajectory. From here you can see for horizontal, you basically just travel at a constant speed. For vertical, I don't want to spend too much time on how to do this, but basically it's a free fall. The formula is given by 1/2 gt squared. Roughly, it's going to be 1/2 g is 10, so 5t squared. If you should have known this before, but if you don't, just try to Google. Okay, free fall. And that's not our focus here. Okay. But either way, we now know the formula of the horizontal trajectory as a function of t. We now know the formula of the vertical trajectory as a function of t. Then, the whole motion, the trajectory, can be described by as, if you put them together, x as a function of t is 2t, and the y is going to be 5t squared, coming from the free fall. I claim this tells us everything about the trajectory. For example, what happens at t equals 1? Well, at that moment, my x is going to be 2, my y is going to be 5, so I'm at point 25. Maybe somewhere here. Okay? What happens at t equals 2? That happens when I have x equals 4 and y equals... Oh, hold on a second. This one is going to be how much you travel, but the whole thing is going to be minus from 10 because you started from... minus from 30. Because you started from 30. Okay, so free fall, you technically don't go down. So you start with 30, you keep going down. Okay, so let's take it back. And here's 5t squared. Okay, so what happens when after you travel for 1 second? Well, x equals 2 times 1, which is 2. Y equals 30 minus 5, which is 25. So after 1 second, I'm at the point 225. What about after 3 seconds? After 3 seconds, what's going to happen is my x is going to be 6, my y is going to be 30, minus 5 times 9, which is negative 45. 30 minus negative 45, which is roughly negative 15. That means I should be at the point 6, negative 15. But then we have a negative height. That actually corresponding to if this trajectory keeps going. So we need to put some restrictions. That is, once your y hits 0, you don't go down anymore. So actually this will never happen. The furthest I'm going to travel is when my y hits 0. Okay, then y equals 30 minus 5t squared equals 0. This gives you t squared equals 6. That means the whole traveling time is going to be square root of 6. So, to describe the motion, we can actually use this one as a formula, and we can tell people we start from t equal to 0, go all the way to the square root of 6, and that should give us the trajectory. Because if you plug in any t between this interval, you will have the corresponding location. That means you know every single location starting from here all the way down to here. Sounds good? So that tells us everything about this trajectory. Of course, we want a formula y equals x. Well, that's not too hard to do. If I know x equals 2t and y equals 30 minus 5t squared, here I use the same t, right? That means my t should equals x over 2 from the first one. And if I plug in the second one, my y should equals 30 minus 5t squared, which is 30 minus 5 over 4x squared. And do you recognize what this is? It's a quadratic. Okay. Moreover, it's a parabola. So this is the reason why all the free fall combined with a horizontal or even soaring with a initial velocity at any angle eventually will give you a parabola, as long as you assume you neglect all the air resistance and the only force on your object is going to be the gravity. Then you will always have a parabola, and here's the reason. Okay, so let's wrap up what we did. We have a motion, which is y equals fx. We want to know what this fx is. What we did is we decompose it into a horizontal, xt, and a vertical, xt. We end up with a formula, x equal to something, one function of t, and then y equals another function of t. Up to here, we already know everything about the motion, but then we say, hey, if we want, we can convert them into y equals fx. That is what we did from here to here. Then we know everything about the trajectory. Okay, that's what we did. Now, this is a curve. But as we said, this is also a curve, which defines the same curve, because as far as we can see from here, we know every information about the motion. Now what we want to do is, we don't want to do things at this level. Instead, we want to backtrack and say, hey, how about we do things at this level? Now let's see what we have here. We have a function, actually two functions. One function tells you x, one function tells you y. They all rely on a third parameter, which is called time, t. If you think about the trajectory is in x and y plane. There's no room for t, right? There's no t here or t here. So basically, when you see a trajectory, it's nothing but a relationship between x and y. But now what we want to do is we want to take a detour. X has some relationship with t. That is x equals 2 times t. Y have some relationship with t. So instead of telling you the relationship between x and y, we actually tell you two relationships. That is the relationship between x and t and the y to t. And use this t to determine what is x and what is y. That is called a parametric equation. Okay, here the variable t is called the parameter. In this case, it is the time. Okay. And for most of the cases, you will see time a lot. Okay, so let me say it again. Here is one way of represent the trajectory. Here is another way, after we simplify everything, to represent the same trajectory. Okay, this and this. What's the difference? Number one, they both tell you the same curve. Number two, this one have a third parameter, which is t. This one involves 3 variables. This one only involves 2 variables. You have the direct relationship between y and x. This one, you take a detour. Instead of taking x and y, you take x to t and y to t. But in this way, hiddenly, implicitly, you already know the relationship between y and x. That is called a parametric equation. Okay? So to give you the definition, basically for parametric curve in 2 dimensions, our x is a function of t, our y is a function of t, and if we combine them together, we can actually represent any kind of trajectories. Sometimes, if it's finite, we want to actually give the range of t. You can think about it as a time. We only care about what happens from now to 2 days later. Or we only care about what happens from the last month to this month. You give it a range. This t here is called a parameter. In our case, we only have one t. Sometimes you can have 2 parameters, t and s, sometimes 3 parameters. Also, we only care about the curves in 2 dimensions, but for curve in 3 dimensions, if you think about it, it's actually really easy. You just add another function, tells people as your horizontal and the vertical things change, how does the third axis change according to the time? So you can connect them together. From here, you can see the advantage because you simply just add one more. Okay, so that's the idea of parametric equations. Let's see several examples. Okay, the first one is let's try to do some examples of parametric equation. Try to imagine what it is. The first one, x equals 2, y equals t. What is this? Let's think about it. Let me put a thing here. 0 less or equal than t less than 3. Okay. What does this tell you, or can you draw it? Well, since t is going from 0 to 3, what we can do is we can plug in t for several numbers. So if t equals 0, I'm at the point 2, 0. If t is 1, I'm at the point 2, 1. If t is 2, I'm at the point 2, 2. Right? Then you start to see the pattern. That is, my x is basically all the time the same. It's always 2. But my y value, which is t, can run from 0 to 3. So what you see here is actually nothing but a segment going from all the way from 0 to 3. That's what this parametric represent. Okay, using the same idea, can you represent a horizontal line? Then a horizontal line is nothing but y equals 3, for example, and x can be anything. And if I don't put any restrictions, my t can be anything, positive or negative. So here is 3. My x, however, can be anything, as long as you keep your y to be 3. This is what this parametric equation represents. Compared to, we just say y equal to 3 for the xy equation. Okay, let's try the third thing. X equals t and y equals t. Your t can be anything. What does this one give you? Well, take t equals 1, you have 1, 1. Take t equals 2, you have 2, 2. Take t equals 3, you have 3, 3. Then you should realize whichever t you plug in, your x and your y value will be always the same. Do you know the points such that you know the x and y value are always the same? Actually, that's everything on this straight line. Alright, so this one actually represents a straight line with 45 degrees. That is pretty nice. But why don't you just use y equals x, which is represent the same line plus it's shorter? Why do you want to add a parameter? And here's the interesting thing. This one does not only tell you the trajectory. Now imagine there is a particle. Okay? This is actually a motion. At t, which is time, equals 0, this particle is at 0, 0. At t equals 1, this particle is at 1, 1. Okay? And then as your t change from 0 all the way to infinity, can you actually kind of vision this particle is moving along this line? As your t start to actually change from 0 to infinity. Okay. That is actually the beauty of the parametric equation. If, let's say, if you start to add additional information about the time, not only you tell people the trajectory, you also tell people how that particle move on this trajectory. Okay? We will see a lot of examples later why introducing a parameter will give you something really interesting. But that's just something we have here. Okay. Now we have some line. Can we have some other line? For example, what if I want the slope to be a little bit like this? Okay, a little bit bigger than t. Well, think about what's going to happen. Why do we have a 45 degree here? That means your horizontal and vertical just travels at the same speed, right? The increase at the same t. If your t is 1, my t is 1. So now all you need to do is just tell people, this time, if I, instead of 45 degree, I want to be above 45 degree, I just need to let my y to move a little bit faster than my horizontal. Okay? Now let's see what happens to this. If I just put a bigger number, this is 1, this is 2, so I pick a bigger number here. That means the vertical is faster than the horizontal, right? That's the velocity, if you think about it. Then what's going to happen is, if t equals 0, 0, you still start from here, but if t equals 1, my x is 1, my y is 2. My x is 2, my y is 4. So actually, every time, your y travels twice as fast as your x. That means no matter what you do, this thing here will be always twice the size of your horizontal. That just gives you another line with a slope. K equals 2. So by manipulating the numbers here, you can actually change the speed of y. By manipulating the number here, you can change the speed of x. And by giving the ratio of this number over this number, you will actually know how y's relationship compared to x speed. You will have actually a certain slope. Okay? I will just keep it here, but from here you can see, basically we can change the slope by just changing the two numbers here. That is the beauty. Okay, let's try another one. Actually, let's just stop here. For straight line, I think it's straightforward. Okay. So maybe so far it's still hard for you to imagine what's going on. You definitely want to associate this thing with what we had before. For example, you want to associate this one with this, so we know it's a line. You want to associate this one with y equals 2x, so you know it's a line. So let's see, how do we transfer between these two type of things? Okay? But before that, let's try another example, which is quite important. How to draw the graph of a parametric equation. These things are easy. Okay. What about the harder ones? And here's the logic. Number one, do you remember how you draw the equation, the graph of anything, you actually draw it by points. You plug in several numbers here, and then you start to say, hey, I got all the points here, and then I connect them together, right? The same logic works for parametric too. So the first job to do this is actually try to draw some points. Okay. Or in another word, how do you determine if a point is on the curve or not? For example, give me several points, which is on t squared minus 1 and 3t over 2. Well, how do you know what point is on this curve? Well, you just simply say, hey, t equals 1. This gives me my x is 1 squared minus 1, which is just 0. And my y is nothing but t equals 1, which is 3/2. So this point is on it. T equals 2. Okay. I'm going to have 3, which is 2 squared minus 1, and then this, which is 3. So getting from these two formulas. From here, you can see if you plug in a single t number, you actually get both x and t, because x and y, because they're the same. They satisfy this equation. Therefore, pick a t, you got a point. Pick a t, you got another point. Sounds good. I'm just going to put some examples here. Okay, x equals 1 squared minus 1, 3 over 2 times 1, which is 0, 3/2. You can do more by yourself. Okay. Now another question, that is, let me call this star. Is the point 5, 6 on the graph of star? Is it? Well, you can ask yourself this question, right? Is the point 5, 6 on the graph of star? I just wonder, can I find a t? Okay, maybe some number. If I plug in star, I will get 5 and 6 at the same time. Okay, that's what I'm trying to do. Then, how do I make it happen? I just let y equals 3t over 2, and I want this one to be 6, right? That means in order for that to happen, my t should be 6 times 3/2. No, divided by 3/2 times 2/3 equals 4. In other words, if you take t equals 4, your y will be 6. But if you take t equals 4, your x, according to star, is going to be 4 squared minus 1, all right, which is 15. Therefore, 15, 6 is on the curve when t equals 4. 5, 6 is not on the curve because I cannot find a t to satisfy 6 to be y and 5 to be x at the same time. To satisfy 6 to be y, my t has to be 4. Okay, so let me organize it a little bit. How to show that this one is on the graph and this is not on the graph? We just try to find this t. Okay, you can either say find the t such that my x is 5, that give you 1t, and then plug in y and try to see do I have 6 at the same time. Or you can plug in y equals 3t over 2 to get 6 to know the t such that your y is 6. Then plug it into x and see if it's 5. Either way works. For this case, the easier one is actually try to calculate y. So, my y is going to be that. This implies my t has to be 4 in order for 6 to happen to my y. Now, simultaneously, do I have 5 in x? Well, I have 15. Is it 5? Not 5. Therefore, 5, 6 is not on the curve. That's how we do it. So if I give you a random point, give you a formula of parametric, you know how to find several points. You just plug in different value of t, you will get different points. Draw them. Okay. If I give you a point, I ask you, is it on the graph? You basically just plug in the y value or x value to solve for t, and then plug in the other to try to see, do I get both numbers at the same time with the same t? Okay, that's how we try to do this. Okay, so with that in mind, you can draw any graph of parametric equations by drawing several points and connect them. And of course, it's not the best way. Now the third one is kind of interesting. That is, can you convert? Okay, let me put it more carefully. Convert a parametric equation the original equation we did, which is y equals fx, because we have learned this one so much. So if we see something, we can recognize this is a circle, this is a straight line or something. So if we have a way to transfer any parametric equation back to this, we will be able to see it. So let's see the example. Let's see the first direction. Can you take a parametric and change it to the old format, y equals fx? Let's press everyone. Number one, x equal to t, y equals t. Okay. Before we know this is a straight line, remember? And we did it basically by drawing several terms and then several points. Then we realized, okay, your x, y are all the same. Okay. But now if you think about it, basically what you're trying to say is x equal to t, which means t equals x. All right. So if I solve t from the first equation and plug t here into the second equation, you can see the t will be gone and x will remain. So what I have here is simply t equals x, then y equals t equals x. This gives you the formula y equals x. So even if you don't recognize this is a line, you definitely recognize this is a line, and through the computation, they're the same. Okay, let's try another example. X equals 2 plus t, and y equals 1 minus 3t. What is it? It's kind of hard to see, but worst case, we just go from the first one. T equals 2 minus x. Okay. Then my y equals 1 minus 3t, which is 1 minus 3, 2 minus x, which equals 1 minus 5 plus a 3x, which equals 3x minus a 4. What is this? It's a line. Then therefore, this is a line. The slope, something is wrong. X minus 2. My apology. Okay, the slope is given by -3. Okay, this is a line. So this is a line. Okay, what about this? X equal t minus 1 and y equals 3 minus t squared. Same thing here. That means t equals x plus 1 and y equals 3 minus t squared, which is 3 minus x plus 1 squared. You can simplify or you don't have to simplify, but I think you already recognize this is a parabola. Therefore, this is the formula of a parabola. Even though you may not recognize it at the first glance, you can always transfer them back. Okay? So from here you can see, knowing the relationship between x and t, and y and t, you can find implicitly the relationship between x and y, because t is a function of x. And then y is a function of t, so of course y is a function of x. Okay? Now let's try something a little bit trickier. X equals cosine t, and y equals sine t. Okay. This one is a little bit more trickier. But let's imagine what's going to happen. Okay, let's try to do something. When t equals 0, what do we have? We have cosine 0 and sine 0, which is 1, 0. Okay. When t equals, for sine cosine, you probably want to try pi over 2. That will give you cosine pi over 2 and sine pi over 2. You can try the other one. You have these 4 points. As your t become bigger, your t travel from here. Your point travel from here all the way to here, and here, and here, and here, as your t change from 0 all the way to 2 pi. Okay, that's interesting, and this is clearly periodic. After every 2 pi, the whole thing repeats itself. Okay. Now, does it look familiar? If you think about it, this is actually the definition. If I simply change your t to another letter, that is x equals cosine theta, and the y equals sine theta. This is exactly the definition of the cosine theta and sine theta, right? So what you have, technically, is just the unit circle. And if you're on the unit circle, your x is actually given by cosine, and your y is actually given by sine, of this angle here. So not only this is the parabola equation of a circle, moreover, the t here corresponds to the angle here. So this is actually a circle. As your t go from 0 to pi over 2, actually this circle, this particle is moving along this way, which is counterclockwise. Okay, again, and again. So this describes a motion on a circular motion. Okay, going counterclockwise. Awesome. But how do you transfer this one to an xy equation? Now ask yourself, if you know x equals cosine t and y equals sine t, you want to find the relation between x and y. That's equivalent to find the relationship between cosine and sine. And what equation do you know that cosine x and sine x satisfy? The trig identity. Therefore, no matter what t, cosine squared t plus sine squared t equals 1. Therefore, this one corresponding to the formula x squared plus y squared equals 1, which is a circle, and which is the same as what we discovered here. So this is a unit circle. From here you can see it's kind of tricky, okay? Can you do something similar? Well, if x equals, probably not c, secant squared t, secant t, sorry. And y equals tangent t. Do you know a trig identity? Yes, you do. Then what you know here is actually secant square minus tangent square t equals 1. This gives you x squared minus y squared equals 1. This is the parametric equation of this thing here. Okay. And I don't know if you have learned this before. What's the form of this? What's the shape of this? This is going to be a hyperbola. Oh, really bad drawing. This is going to be a hyperbola with 45 degrees. And basically you have this part, you have this part, and then the t you're talking about is nothing but here. The angle here. Okay, then you're going to see a particle traveling this way as your t becomes bigger and bigger. And eventually, remember, your t goes to pi over 2, your y is going to be infinity. That means you're actually at the very end here. But right after you go past pi over 2, your particle will actually show up here and then start to travel on this one. Okay, so, actually the other way around, from here and then start to travel in this way. From here you can see you have a particle. The motion is described by this motion here. Basically the particle starts from 0 here, travel all the way up to the end of the world, and suddenly jump to here, reappear, and then start to travel in this way. Okay, which is some motion you could not easily see from here. Okay, that's enough example. In general, this thing can be really, really tricky. So, yeah, I don't know. You probably just need to want to do more exercise. But the key here is, given these two formulas, and to try to establish a relationship between x and y. Okay. So that's the direction. If I give you parametric, can you make it a regular formula? Now let's see if I give you a regular formula, y equals fx. Can you transfer it to a parametric? And is it always doable? Well, for example, if I give you something which is y equals x squared, can you transfer it into a parametric equation? Well, the answer is you can always do it. Let me change it. Let me change it to be y equals x. Let's go with x squared. Okay, y equals x squared. Okay, worst case, you just define your x to be t, and then you know y as a function of x. Then you know y as a function of t. If this is x squared, this is t squared because my x is t. This is already a parametric equation, which is not a great one, but it is. Okay, which doesn't make sense at all because basically you just change the name of a variable, but that's a parametric. But then this thing becomes interesting. If this is going to work, I can also change x equals 2t. Okay, then my y is just going to be 4t squared. It's the same equation here, right? They satisfy the same equation. Okay, from here you can see you have all kinds of ways of doing it. You can also have x equals cosine t, and then y equals cosine square t, which is still y equals x squared, because your x is this, my y is nothing but the square of cosine t. From here you can see there's no unique way of doing this. Okay, but number one is, what's the difference between all these? Number two is there an easier one? If all of them make sense, which one should I pick? Okay, to see the difference, you probably want to start with something very simple. Let's start with this one to illustrate. This is clearly a straight line. Okay, clearly I'm just going to pick two, the parametric equations. The first one is x equals t, y equals t. Okay. The second one is going to be x equals 2t and y equals 2t. And then the third one is going to be x equals cosine t and y equals cosine t. They all satisfy the same trajectory. Which is y equals x, which is this 45 degree. Okay. But what's the difference between this one, and this one? Let's check the first two. It's easier to compare. Number one, they all pass the same point. Okay, so there's no point to check, are they the same? They're all the same in terms of trajectories. But if you think about the comparison of these two, right? If you plug in t equals 1, what happened? This point is going to travel from 0, 0, let's name it 1, 2, 3, all the way to 1, 1. But if you plug in t equals 1 in 2, 2 traveled from 0, 0 to 2, 2. That means this one went from here to here. If you take t from 0 to 1. But the second one took the same trajectory, but went here. Okay. Can you see that? Basically, they share the same trajectory, but 2 is faster than 1, where the speed ratio is exactly twice as faster. Because every time you have x, I double your value. Every time you have a y, you double your value. And if you think about in trajectory, this is basically the speed, right? It's a constant speed times the time. So if you start to manipulate things in this way, even though y and x satisfy the same relationship in 1 and 2, it's both y equals x, but they have different speed. Sounds good? Okay, so that's the first interesting thing you can have. From here you can see, you can actually change it even to this. 3t and y equals 3t, which will be even faster than 2, or 4t and 4t, which is in fact be even faster than 3t. Okay, you can change whatever speed you want, even though it's for the same trajectory. You can even do this. You can take x equal to t squared and y equals t squared. What's going to happen with this is this particle will initially move really slow. But once they pass 1, t squared will be bigger than t. That means at first it's slow, but eventually it becomes faster and faster and faster, because square just grows faster. So you don't have a constant speed anymore. You generally add to your acceleration. Oh, you have an acceleration. Generally you actually add to your velocity, which means you travel faster and faster and faster. Okay, that is good. What about the third one? This one's even more interesting. Okay, let's think about it. Number one, we all know -1 is less or equal than cosine t and less or equal than 1. That means even though this one travels the whole trajectory on the trajectory y equal to x, but it never go beyond horizontally to here and vertically from here to here. It never go beyond that. So you're only talking about a part of the trajectory. Second, you don't know the motion, but do you know how x change with respect to t? Your horizontal trajectory is just a wave, so your x is going to travel like this. here, 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 here. Just back and forth, and back and forth. Similarly, your y is going to travel like this. They travel back and forth. But remember, when you put x and y together, both of them oscillate, but they have to oscillate on this trajectory. Then what's going to happen is you are going to have a particle. The particle is going to go to this side, and then come back to this side, and then start oscillating between these 2 points. Okay? So even though this one gives you the same trajectory, but it only take parts of it, plus on this trajectory you actually keep oscillating. You never go all the way to infinity. You don't do that. You just come here and come back. Okay? And that is a different motion. Hopefully everything makes sense so far. But if that's the case, you can see how much more information parametric equation contains than the original one, y equals x. Because if you just give people y equals x, you tell people, well, there's a particle. The particle has traveled there yesterday, and then the particle finished traveling, and then I go there and look. I see all the trace the particle left. It's a trace like this. Okay? But you couldn't tell, did the particle just, finish really quickly? Or did the particle just actually took the whole day to get there? Or did the particle even actually went to more than one cycle? All you see is just what's left from the motion. If you just take this representation. It's almost like, you have a color particle which can leave a trace when they travel. You let the particle travel without looking at it, and when it finished traveling, you come back and try to see the trace. Okay. However, if you give it a parametric equation, you put a t there. Not only you know the trajectory, you also know how the particle actually traveled along this trajectory. You have way richer details about the motion. That's the advantage of parametric. Okay? Now to give you an idea of what we just did, I tried my best to do several things, so let's just take a look. Okay. Let's take a look at the first one. A. Okay. This is the point. I chose the formula to be 2a, x equals 2a, and y equals 2a. From here you can see it's a straight line. But now what I'm going to do is I'm going to let a change from 0 to 20 and take a look at what's going to happen. Okay, now it's playing backwards. Okay. But now if you think about it, what you really have, you do have a line. I probably want a different color, which is the trajectory. But if you use parametric, not only this one tells you the trajectory, it tells you how the trajectory was drawn. That's the move of the particle. Okay. Now, if you think about what we just did, and we'll add another parametric equation, which is just a and a, which is the same trajectory, remember? Okay, that's the blue dot. Okay, let's compare the blue and the red. Keep in mind, okay, the red is 2a on the left top corner. The blue is just AA. They both share the trajectory y equals x, which is 45 degrees. But if you start kick play, you can see the red is always twice the speed as the blue. That's pretty cool, right? Now, as I said, I can also change the blue to be the thing we just say, which is a square and a square, which is again the same trajectory. But let's see what's going to happen. Oh, Desmos, you suck. Okay, oh no, Desmos is great. You see what happened? Okay, let's see it again. Think about it, okay? What's the difference between 2a and a squared? When a is less than 1, you can see a squared is less than a. So at first, the blue dot is going to be slower. Okay. But when a becomes bigger, for example, a becomes 3, then a squared is clearly bigger than 2a. Then the blue is going to be faster. So the blue is going to be slow at first. but faster later. Eventually, it will dominate A. That roughly happens at the square root of 2. Okay. Now, I'm going to ask you a question, and you can think about it yourself. What if I change this to be exponential? E to the A and E to the A. It's going to be even faster than a polynomial non-quadratic. So you can see at first the blue is going to be super slow. But once it hit 1 or maybe 2, the blue is going to be just disappear right away. Okay, because it's so fast. It traces all the way to almost infinity. That's the beauty of this. Now, we can go back and think about what we have. That is when I say, what if I have cosine? I didn't write it down, so let's just do this. What if I have a cosine A and a cosine A? Okay, let's take a look. The red dot, it's still the same trajectory, right? But look, let's focus on the blue just. Okay. You see what's happening with cosine A? Okay, now it's backwards. Okay, forward. Because your x oscillate, your y oscillate. But again, you still follow the green trajectory, so you still have the same trajectory, but your motion are quite different. Okay, that's the beauty of it. Now let's check another one. Look at the green. The green we have here is going to be a and a squared. That means your y is basically x squared. So that is going to give you a trajectory. Oh my god. Okay, y equals x squared. It's going to give you a trajectory like this. But let's see how the parametric equation gives you the motion. When a equals 0, it's at 0, 0. You see that motion here? Okay, when you put it backwards, actually, you can see even more. Because square grow really fast, so the graph will look really... Okay. Now, if you change the a to be a different thing, for example, it's the same trajectory, but cosine a and cosine square a, it's still y equals cosine square. Now, try to imagine what's going to happen. Okay, you still follow the trajectory, but you go back and forth, back and forth, back and forth, because your x chose to go this way. That is beautiful. Okay. Now the third thing is cosine a and sine a. We already know it's gonna be a circle, right? Plus y squared equals 1. The black is the circle. Let's change it to be orange. Okay. Now if I click A, you can see this point start to travel this way. Okay, now it's backwards because my A hit the end and started to go backwards. Great. Now what will happen if I give, instead of 2A, I give it a 3A? Think about it. You will still have the same trajectory, right? The only difference is for the same A. Now this 3A is going to be faster. Let's focus on it. Okay, can you see the black dot is traveling at the speed of 1? And the red is actually traveling at the speed of 3. Okay, from here you can see they share the same trajectory, but that's clearly different motion, which a simple x squared plus y squared equals 1 cannot give you. You need to have a parametric to indicate the parameters. Okay, it's either time or in this case it's an angle. We can even have something more interesting. What if I just change both of them? I let x to oscillate and y oscillate. Before they oscillate at the same frequency. Now I want one oscillate at 5 and the other one oscillate at 3. What do you think the shape is going to be? Hold on. I should put this one down. And probably I want to slow down my motion a little bit. Let's just take a 10. Slow it down. You can see it's not a circle anymore. But if you just look at the horizontal still oscillate. If you look at the vertical still oscillate. Up and down, left and right, left and right. It's just they don't have the same frequency, so they don't have a circle. But what do they have? Actually, they have a trajectory like this. Okay? This is exciting, right? If you wonder what's going to happen, you just simply go there and change this 3 to be a 4. Oh, sorry. What is it? 3. Okay. I want to change the trajectory here to be a 4. Okay. Change this one to be a 8. Change this one to be a 10. Oh, 10 is probably not a good idea. 11. Okay. You can have all kinds of interesting shapes formed by this. You're going to follow a different trajectory. I don't even want to bother, but let's just take a look and appreciate the beauty. Okay, how does this one is going to move? You don't even know which. It's too fast, right? But you can, because the frequency, the oscillation is really fast. But you can roughly see like it still follows the trajectory here. Okay, that's the beauty of doing parametric. You always have all the details of this motion. Okay. Okay, by the way, I just showed you some interesting graph, and you can actually play with decimals by yourself to define some more interesting graphs you can have. Just to make sure, if you put t here, decimals is going to recognize this is going to be a parametric equation. They're going to give you the curve. So if you want to add a slider to see how the particle works, you probably want to use another letter like A. And then now we actually start to track only the point. Yeah, let me put. Okay. Otherwise, if you take the same formula and give it a t, it will actually show you the whole trajectory, not just like a single point. Okay, and you cannot add a slider of t. Okay, so try to play with it and try to be creative, find something. This is really fun, actually. Okay. I think we have the basic. What is a parametric equation and what can it do? And also, if you see a parametric equation, you can transfer it into our original equation, which is yx. But now we know actually parametric equation have way more information because it also included how the particle is going to travel through the trajectory. And you can imagine in 3 dimensions, this is going to be even more handy because 3-dimensional curves can be really complicated. Okay, now what's left? Well, we want to show some typical parametric equations. That means there are a lot of parametric equations, but you are required to be at least understanding 2 types of them. The first type is going to be straight line. And it's very easy to understand. The formula is going to be given by x equals a plus ht and y equals b plus kt. Okay. Here, a, b, h, k are numbers, real numbers. Okay. Let's see what each one does. For example, if I take x equals 2 plus t and y equals 3 minus 4t. Okay, this is a straight line with your a and b to be 2 and 3. Your h equals 1 and your k equals -4. So that is actually a formula of a general line. You have 4 numbers. 2 with t and 2 without t. Okay? Now, what do these numbers tell you? Let's take a simple look. Number 1. Plug in t equal to 0. When you plug in t equal to 0 in this format, you will realize this term and this term will be gone. Then it gives you x equals a and y equals b. From here you can see a and b simply tells you 1 point. Okay? A point happens at t equals 0. So this gives you a point from the straight line. For example, for this particular example, let's call it 1. Then basically it tells you it passed the point 2, 3. Why? Because if you plug in 0, you got 2, 3. Okay. Now without this 2, 3, let's talk about what this t and the minus 4t give you starting from 2, 3. Okay. Take t equals 1. What's going to happen is, this one tells you you start from 2, 3. You add a 1, and you minus a 4 here. So you go 1, you go down by 4. So this is going to be 1 and negative 4 if t equals 1. If t equals 2, this is going to give you a 2 and a minus 8. So there's a 2, there's a minus 8. Does it make sense to everybody? From here you can see the ratio between these two numbers basically tells you if your x move by 1, how much does your y move? In this case, your y move by negative 4. Together, you know this means the slope is going to be negative 4. Kind of makes sense here? Okay, from here you can see, next time you see something like a straight line, first you need to recognize it is a straight line by recognizing the 4 numbers and the t. Second, a and b actually tells you a point on the line, which give you what happens at t equal to 0. And the k over h, which is a ratio, gives you a slope. This tells you if your x move by 1, how much your y will move. Okay, maybe twice the size of your x, maybe 3 times the size, maybe 1/3 of your x, and also maybe if your x increases, your y is going to be decreasing. That means your slope is negative. Okay, let's recognize really quickly. So let's go back to this one. So just by looking at this, I kind of know, okay, number 1, this one passed the point, 2, 3. And this one has a slope, negative 4 over 1, which is negative 4. So if you take a look, let's transform this one into the original xy equation. So remember what we do? We solve t from the first x, and then we plug in t using x minus 2, which we just solved. We have 3 minus 4x plus 8, which gives you 11 minus 4x. From here you can see the slope is negative 4, as we said. And if you plug in 2, you got 11 minus 4 times 2, which is 11 minus 8. You do have 2, 3. Okay, so you do pass the point 2, 3. So these are the information contained in this straight line. For example, go back to what we did before. What is this? Well, this one passed 0, 0 because your AB and 0, and your slope is going to be 1 over 1, which is 1. So that's the 45-degree line, which is y equals x. Okay, so that's the idea of the straight line. What if you have x, y equals 2t and 2t? Now you can see when we say h over k is the slope, we really just care about the ratio. You can have 3 over 3, you can have 2 over 2, you can have 1 over 1. They all give you a slope of 1. And we know that is true. So basically, the ratio gives you the slope, which is the trajectory, but this additional number, as long as they give you the same ratio but they are different number, they are going to give you the same trajectory but different speed. So tt goes this way, 2t also goes this way but faster, 3t also go this way, which is faster, but the slope stay the same, which is 1. Okay, so that is the straight line. Next time you see something like that, you should be able to read the information right away. Also, if I ask you to find the parametric of the equation, let's actually do one. Okay, example. Oh, this is going to be number 4. Okay, find the parametric equation of a line passing 2 points, 2, 3. Let's do 1, 4, and negative 2 and 6. Okay, now let's write it down. The formula is given by this: a and b plus ht and kt. Our job is try to find a, b, h, and k. Now a, b is a point you have, so you can just take it right away. xy equals 1, 4 if you take 1, 4, or you can take xy equals negative 2 and 6. It doesn't really matter which one you take. Okay, and then what you need to do is you need to figure out k over h. Okay, k over h is your slope. What did I say there? Did I say h over k? Oh, I said k over h. Okay, so that is good. Great. I may have said it's h over k, but it's that technically k over h. So, but from logic, we technically know the derivative k over h is going to be 6 minus 4 divided by negative 2 minus 1. Then you are going to have 2 over negative 3. So you just pick any k, which will work for this one. For example, you can pick k to be 2. Remember, k is the one with y. And your h bit to be negative 3. This one clearly give you negative 2/3. Okay? Or you can take it to be negative 6t and plus 4t, which also give you negative 2/3. So you just need to keep the ratio to be the same. And if you pick different pairs, which give you the same ratio, that means the trajectory stays the same, but you have different speed. This one is faster. Okay? And do you believe? From here you can see you have two very different parametric equations. They share the same slope, and they pass two different points, but they're both on the same line. You can verify by yourself. Okay? They are actually equivalent. You draw it through Desmos, or you draw it by yourself. They are actually the same line. But your particle is going to move differently. They start at different position. When you plug in t equal to 0 for this motion, it starts from 1, 4. For this motion, it starts from negative 2, 6. Moreover, this one on the right is faster because you have a faster speed, even though it's the same trajectory. So in the exam, pick either. I just need you to do one, and then without restriction, then I'm just going to tell you it's going to be this one. You can create one, and the answer is not unique. Okay. Now the second thing you need to know, which is almost like a standard, are the formula of a circle. So what is a circle? Well, you can easily see x equal to cosine t, and y equal sine t. That's our, our candidate for a circle. This one certainly works for this unit circle. Now what you want to do is, and you can see actually this is a unit circle, negative 1, negative 1, 1, 1, okay? Now you just want this one to move in this way. Now for general circle, you have two things, informations. The first one is your center can be anything, A, B. It doesn't have to be in the center of 0, 0, which is the origin. Second, your radius can be anything. For unit circle, you only have one. So how do we put those kind of information into this formula? That's the next thing. Okay, let's talk about the radius. What do you mean by the radius? Well, if your radius is 2, that simply means your x squared plus y squared equals 4, right? But if you just do this, there's no way you can have a 4, you can only have 1. So you need to multiply it with a different number, that is 2. So what you need to do is just put the r here if you have a radius different than 1. For example, if you pick r equal to 2, then 2 cosine t, which is your x, plus 2 sine t, which is your y, will give you 4, which is 4 x squared plus y squared equals 4. So you simply just, if you want to double the radius, you just double your x, double your y. That would work. Okay. Second, once you put r here, you are going to have a circle centered at 0, 0, but with a radius r. Now you want to move this circle to any arbitrary center, which give you a here, b, and give you b here. From here you can see you basically take the same x, but just shift it to the right by a. You simply just put a plus this. We'll take whatever you have from here, shift it to the right by a. Similarly, you can take a b plus, which means take whatever centered from origin and shift it up by a b. So that is the general formula of a circle. R cosine t equals b plus r sine t. AB give you the center, okay, and r technically give you the radius. And I think we don't need examples. It's super easy to understand. Okay. Now some of you may have question. Right, x squared plus y squared equals 1. That's great. From here, you kind of said x equal to cosine t and x equal to sine t. Because clearly this is one way to find the parametric equation. They satisfy this equation. But what if I switch x and y? I take x equals sine t and take y equals cosine t. Well, it still satisfies this one. So they should have the same trajectory. But clearly they are different formulas, they are different motion. So what's the difference between if you just switch x and y, which still satisfy this? Actually, there is something more you can do. You can even add a negative sign on this. Kind of makes sense here. It still gives you x squared plus y squared equal to 1. So you have all these kind of ways to parameterize all the same circle. To see that, there are multiple ways of presenting it, but I'm just going to show you this. Okay, let's delete this. Let's delete that. Let's delete this and that. Now, this is a circle. As we said, it just moves like a circle. Yeah, somehow I stretched this thing. It's not a square anymore. Right, but you can see it's I better just, oh, yeah, here we go. You can see it's a circle. Okay, let's say it again. It's a circle with radius 1. Great. Now what if? Yeah. Okay. Stop. Now what if I switch the x and y, which still satisfy the same equation, but clearly a different motion? So let's put a, comma, cosine a, comma. Okay. You see the difference for the red and black? The black is the old one we have, cosine, sine, and the red one is actually the one we have, sine and cosine. From here you can see these two motions. Number one, they start from different point. You take a equal to 0. You start from 1, 0 for the black circle. You start from 0, 1. No, yes, 0, 1 for the red circle. But now if you let things move, and pay attention here, black and red, and see the difference. Okay, let's say it again. Can you see that? Yes, it gave you the same trajectory, but they start from different initial points and their orientations are different. One goes clockwise and one goes counterclockwise. You can play with if you just have a negative sign here. That will change things even further. But no big deal. You can play with it by yourself. Now you can see the red start a little bit different. Before it start from, okay, let's see. Now it's counterclockwise again. And put another negative sign at random places. You can experiment by yourself. From here you can see there are all kinds of ways you can represent a circle. But by convention, we go with x equal to cosine and y equal sine. Just by convention. All these will work, but they don't necessarily give you the conventional starting point. It doesn't necessarily give you the conventional orientation, which means clockwise or counterclockwise. Okay, so that's the only difference. So we choose to go with this, but all these will be correct if we don't specify the orientations. Okay, I think everything so far should be good. It's all organized in your notes. Now we want to think a little bit about the advantage of using parametric compared to the original functions we have. For example, let's take the easy one. We have one way of parametric. We have the non-parametric way. Which way is better? Well, the first advantage is both of them give you the same trajectory. But as we said, this one contains more information. It tells you where the motion starts at t equal to 0. It tells you which way it moves and how fast it moves. So you can track the motion. That's the first advantage. Okay? It tells you the motion. Second advantage is you can have some flexibility. For example, for some motion, let's take a circular motion. To describe the motion, you can track multiple things to give you the same motion. First of all, you can track the time and give x and y as a function of time. That's totally fine. You can also track this theta and give x and y to be a function of theta. That's totally fine. You can also track the arc length L and give x and y as a function of L. From here you can see you have multiple choice of different parameters and each one give you a different formula. And then under some kind of things you want to study, one of them is going to give you the convenience. For example, if you really care about the angles, probably and angular speed, probably you want to pick theta. If you really care about the arc length, probably you should pick L because that thing is most related to your arc length. So you have the choice of pick whichever parameter you want, compared to you just have x and y. Okay, you can pick time, you can pick angle, you can pick this, and later you can pick other stuff like velocity, you can pick accelerations, and all kinds of stuff. As long as you give the same trajectory and the same motion, actually they all describe the same thing. But one way is easier than the other. The third thing is repeating trajectory, and that is interesting. X squared plus y squared is 1. You just have this circle. That's it, right? Now take a look at these two formula. The first one is this. But t goes from 0 to 2 pi. The second one is this. Same thing. But you have a different range. 6 pi. That means you complete 3 cycles. What's the difference between these two graphs? For the first one, you basically have a motion. This thing starts from here, go here, it stops. Okay. For the second one, you start with a motion. You go for once, it's not enough, you go for another time, and then you go for another time. I try to draw them differently to let you see we did went over 3 times, but of course, their trajectory should be overlaying each other. That's why just going by this, and you may know a particle is traveling through the trajectory, but you don't know, did it travel for 3 full cycles, 3.5 full cycles, 7 cycles? You don't know. You don't even know which direction it's going. That's why this is great. You could never have a repeated trajectory, okay, when you start to do functions like y equals fx. The concept of speed is kind of related to the motion, okay? And the third thing is really interesting. That is the time of events. What do you mean by time of events? Well, let's think about this. If you do y equals fx, do you remember in order for this one to be a function, we have a very strong restriction, that is 1x goes to 1y. You cannot have 1x goes to multiple y. Otherwise, you violate the vertical line test. You're not a function. That's a very strong restriction, right? Which kind of makes sense, right? In real life, if you want to predict something, you put in an input, you have one output. You put in one input, you have 2 output. You don't know which one to take to be your answer. That means all this function has to have this property. That means y equals fx will not give you anything which will have multiple y values. Moreover, you definitely cannot have a trajectory which goes like this, which intersect with itself, and then come back and intersect with itself, and start repeating. In this kind of way, for the same x, you have a lot of y. And that is a very, very bad situation. That means you plug in a location, you say, hey, where is that thing? You say, well, I don't have a unique location. That is bad. But now, if you think about a particle, it's very possible this particle actually travel this way, and then travel again. Okay, and there's nothing confusing about it. Why is that? Because you kind of write your x to be a function of t, and the y to be a function of t. And these two functions, as a function of t, they have unique value. Okay? Think about it. That means at any point, you may hit this point x, y for multiple times, but at a different time. So for a given time, you still only have one position. You don't have multiple positions. It's just after a while, given a different time, you can return to this position. But technically, it's a different position now because you're here at a different time. So you can still keep this nice of one-to-one relationship. Your one time only goes to one location. Okay. Even though multiple locations can happen, multiple time can go to the same location, but it's still fine. But before, you cannot have fun because same location basically means for the same x, you have multiple same y. It's not going to happen. So that's why this one is more flexible. You don't have the restrictions of those. Okay. Now another advantage of time event, we can actually see an example. I probably don't want to write it down anymore. Okay. Consider two motions of two particles. The first motion is x equal to 2t, y equals 2t, and the second motion is x equal to 1 minus t and t. With what we have, we know the trajectory. This one is past 0, 0 with a slope 1. Okay. That is the black line here. The second one. This is the one. The second one, you can take a look. It's going to be passing 1, 0 with a slope -1. So that is actually this red line here. Now look at the first question. Do the trajectory intersect? The answer is yes, they do intersect. Okay, they intersect at 1/2, 1/2. Now you can imagine, here are the trajectories of two particles. Two particles travel through this trajectory. And then you need to ask people another question, that is, do the two particles collide? Which means they appear at the same location at the same time. That means they basically hit on each other. Okay, they may break into different parts, or either way, they will hit on each other. Well, this is interesting. You do know that their trajectory only intersect at one point. So if they do hit each other, they can only hit each other at 1/2, 1/2. All right? But if you plug it 1/2, 1/2 into the first motion, you find t equals 1/4. You plug 1/2, 1/2 into the second motion, you find that t equals 1/2. That means, yes, both particle pass the same point 1/2, 1/2, where their trajectory intersect, but the particle in the first motion passes first at 1/4 second, for example. And then the second particle passed the same location at the time 1/2. That means, if you think about it, that means, yeah, our trajectory intersect each other here. But when my particle is here, the red one is still here. And then when my particle goes here, now the red one becomes here. Okay, going this way, and this one's going this way. So even though our trajectory intersect, but we don't actually arrive at the intersection at the same time, we're still safe. We're not going to run into each other. Okay, so that's what we mean by flexibility of time. Because of time, you know where the particle is, and at a single time, the particle can be only in one position, not the whole trajectory. Okay, so instead of seeing a whole trajectory, you start to see how the trajectory developed. That is here, and then here, and then here, and then here. Okay, instead of just like one thing. That is the flexibility of the time. This is also great. But there's one last one, which is also great. That is, there are some function which is super difficult to find a formula for y equals fx. It's not impossible, but it's really hard. But it's considerably easier to do it in parametric. It's easier. I will show you one example. This one example is very, very, very important. So I wrote down the detailed derivation here in the notes, but I will walk you through it. It's a thing called a cycloid. Okay. I don't know if you have seen this before, but that's a very interesting concept. So consider there is a circle. You can think about it as a tire. Okay. And then this circle actually travels this way. So you can see as this circle moves to the right, this thing starts to rotate. Now I'm going to focus on this point here. Let me make it red. Okay. After a while, you have the tire, but then this one has rotated to here. After a while, this tire is here, and then this point has rotated to here. Do you see what's going on here? So I want to keep track of this one single point. And just focus on that single point, you can realize this single point is going to have a trajectory which roughly looks like this. And eventually go here. That's when you complete one cycle. And then you start to repeat the cycle again. And this is actually a very special shape. You track one point when you let a circle to rotate. And that is called a cycloid. Of course, our job is going to try to find the formula of this one. Okay. Well, what's the formula of this one? We can have a rough idea. Number one, this one starts from here, right? That's when this circle is here. Number two, when this circle rotates 180 degrees, this one is definitely here. And that is actually the peak. You can only go this far. So roughly you raise to here, and then you go down here. Good so far? That's when you have a complete rotation, which means 360 degrees for the tire. And then, according to our experience, the same thing should start to repeat again. And then repeat again. Because simply, with a difference of 2 pi, this one just repeats itself. It's periodic. But that's roughly what we know. Okay. Now, how do you find a formula for this? I'm not saying it's impossible, but it's very difficult to try to find the formula in y equals fx. I will give you the formula. Okay, the formula looks like this. r cosine inverse 1 minus y over r minus y 2r minus y. There's a square root. Okay. I better use capital R all the time. From here you can see it's not impossible, but this one looks ridiculous. Can you derive it? The answer is yes. You need to use a lot of trigonometry, and you need to use half-angle formula, and you need to discuss it by different, situations, because sometimes you take a positive sign when you use half-angle formula, and sometimes you take a negative sign. Okay, so it's ridiculous. Now, what I want to show you is how to get the formula. How to get the formula from a parametric. Of course, in order to do this, we probably want to pick a parameter first. You can pick it to be time. Thinking velocity, it's going to be really hard. But let's see. We just need to do one cycle, right? Then the rest repeats. What has changed during this one cycle? Well, when you talk about cycle, you definitely want an angle. Okay. You want this angle to track the whole rotation of the tire. Okay. You want this angle to complete from 0 to 2 pi for one trajectory like this. So what angle actually changes from 0 to 2 pi in this case? I think it's not hard to see. Let me write it here. Okay. I want to take this angle, which is the angle between the current position of the point and the vertical direction. Okay. So think about what's going to happen, how this angle is going to change during this trajectory. It will start from 0, because at first the point is here. It has 0 degree between it and the vertical axis. When it hit the peak, the angle is going to be pi. And when that thing actually go all the way, come back again, you are going to have 2 pi. And before that, you have probably 359 degree. But here you have 2 pi. And starting from there, that thing repeats. So when you repeat the whole trajectory of like this, my theta went all the way from 0 to 2 pi. So it's settled. My formula is going to be x as a function of theta and y as a function of theta. Okay, and this will work for theta from 0 to 2 pi, and then we release this so you have more rotations for more period. Sounds good? Okay, so that's the parameter we picked because it's really easy to track. It goes from 0 to 2 pi. Now the harder part is actually try to write x and y to be a formula like this. But actually, if we take a look, maybe it's not too hard. Let's think about you start from here. Now your tire is here. Now you start to have theta. Okay, let's make it bigger. Okay. My first question is, how long is this? That is going to be L. Okay. But let's assume your tire is always on the road. Then, a quick observation, I didn't draw it really carefully, okay? Probably I want to redraw it, just to make sure it makes sense. Okay, probably I want to do this here, and roughly something here, which looks more real. Theta, okay. Now pay attention to the two things I draw in green color. Can you see these two green colors should be the same? Simply because your tire never leave the ground. Otherwise, the things start to slip. Okay, then this is L. Then this arc here is also L. Now, think about x if we take this to be the origin. 0. Okay, your x value is nothing but this. Your y value is nothing but this. You just want to write the length of these two to be in terms of theta. Then job done. Good so far? Now here's where the magic comes. Because you have trigonometry, you can extend this one to here. Okay? Can you see that? This angle here is theta. Okay. Now I'm going to write down your x is going to be L minus minus, remember L goes all the way from here to here. Your x only stop here. So it's going to be L minus this, which is D. And your y is going to be R, which is, let me write it down, R minus this. Let's call it H. Okay. Pause and try to make sure you understand what's going on here. Okay. I will show you. This is going to be your y. Y and H together is R. Okay. This is L, which goes from here all the way to here. But that is actually x plus D. So we have this formula. Now, if that is okay, let's try to do it. L, how long is the L? L is the same as the arc length. The arc length is nothing but theta times the radius. What is D? D, if you take this out and try to see the triangle I draw here, this is D, this is H, and this is R by the radius, right? So D is nothing but R, oh remember this is theta, R times sine theta. And H is nothing but R times cosine theta. Good so far? And that's it. You have the formula. X equals theta dot R minus R sine theta. Y equals R minus R cosine theta. For some people, they want to simplify it. So this gives you R, parenthesis, theta minus sine theta. This gives you R, 1 minus cosine theta. That is the formula of a cycloid. And all we need to do is just draw this simple picture and try to do things with trigonometry, compared to a formula looking like the thing I just crossed out, which is basically impossible. Okay, so with that in mind, can you see in this case, because we cleverly chose a parameter which is theta, which is way easier to track than x and y or time, we have a relatively simple formula. Okay, to see how this one works, let's go to decimals and type it out. Okay, now you have x and y, right? So I'm kind of slow on this. Your x is going to be R. Let's just take R to be 1. Okay, and then we just have theta. I'm going to use A minus cosine A, sine A. Okay, and then 1 minus cosine A. Where is it? Okay. Now let's pay attention to. Let's make it longer. Let's go from here to 20. Okay. Let's see how the tire is going to work. Okay, this is backwards already. Let's see forward. Go like that, go like that, go like that, and that's how the parametric thing change. Okay, that's a cycloid. Now note, at first it's pretty slow, and then it's fast, and then it's slow, and then it's fast. So during each cycle, I probably want to do 2 pi here, which is like 6.3. Let's just do 6.3. Step to be really small to let you see what's going on. Okay. At first it's pretty slow, and then faster, and then slow down. Okay, let's look at it again. Slow, fast, slow. Okay, so that's actually how the thing is going to work. Now I'm going to give you a better representation, and I twist the note, type it by myself. But let's do decimals. Cycloid. And they have a nice builder, okay, which give you a way better, but don't trust what they put there, because it's technically not too careful. They're just trying to make this one beautiful, but let's start from 0. And let's end at, I don't know, 40? Okay. Now, let's start. Probably that's too much. Pay attention to the green dot, the orange dot. Ooh. Okay, so that's actually a pretty cool graph, and that is what we call a cycloid. It's not just for fun. Cycloid has a very wide applications. Number one, think about if you have a nail here, and then your nail is actually, let's say your tire hit the nail, and then the tire is going to start to rotate, right? So you will be able to track down the trajectory of the nail, and you will know actually how much force the nail is applying to the whole tire, and then you know how do you actually protect your tire a little bit, or how do you use a sensor to sense did your tire went flat or not. Okay, that's one way. Another interesting thing is this. Let's assume here is a platform, and think about skateboard. Okay. Now here's the thing, or let's just think about a ball first. You are going to have an arc, so this one actually goes down. So if you put a ball here, this one is going to roll down. Sounds good? Okay. Now my question is, how do you design this slope to make this one to be taking the least time? Think about it. You can design a slope like this to be just straight. Then of course it takes some time. But what if you actually let this one to go a little bit like this? So what's going to happen? Well, because this is steeper at first, you can accelerate to really high speed really quickly compared to the straight line. But you do travel further. So you have a faster speed, but you also travel further. So there's no guarantee you are going to have a shorter time or bigger time. So actually you can experiment with all kinds of arc. Okay? The more that it's bended, the faster you can reach the maximum speed. But you're going to travel longer. So the question is, at which shape, you are going to have just the sweet spot, such that the time it takes to roll from here to here is the least. And the answer is cycloid. Kind of makes sense here? Okay, that's one way of doing it. Now, another way to think about it is this. Let's say you have light traveling through different kind of mediums, and these mediums have different density. So after you travel here, the light is going to bend. Make sense so far? Okay. But now let's imagine, not only this light is going to bend, you actually have multi-layers of different mediums with different densities. So this one is going to bend, and then this one is going to bend, and then this one is going to bend further and further because your medium just became denser and denser and denser as you go further. Good so far? So what you can see is actually a trajectory keep bending and more flat. Okay. Now imagine this one goes to the extreme. Imagine the distance here becomes super small. Then almost you have a fluid, let's say, and the density is continuously changing. Here's low density, here's high density. Okay. Then your bending of your light is going to be continuous like this. Now the question becomes, again, what's the shape of this curve? If you let the density of this one change from low to high linearly. Now here's a very simple principle. I think most of you guys knows about it. That is, light travel in the fastest path. This is not exactly accurate, but it's pretty accurate. Okay, if your speed is, if you are not talking about relativities, this is actually pretty good approximation. So fastest means least time. So you're almost asking people, how do you travel from here to here using the least time, assuming this thing is actually linearly changing in terms of density, which is actually exactly the same format of this when you try to roll a ball and down. Therefore, this is going to be a cycloid too. Okay. There are many other applications, but I think these two are the most important and interesting. So go back to the notes. I wrote all the derivations of how you got this formula from here. And this formula is covered in the exam, so you do need to know this. This is an example to show you there are some kind of motions which is really difficult. Okay, some formula which is really difficult to find using y equals fx, but it's relatively easier to find using parametric, because simply you introduce another parameter, and that parameter may be super easy to track compared to if you want to track x or y. That's all for today. Next time, with all this kind of new way of describing a motion with a curve, now we want to define what do you mean by the derivative, okay, of a parametric equation. We know how to define the derivative of f prime x from here, right? It's just like the difference quotient, whatever. But if your formula is given by this, especially if you have a t, how do you take the derivative with respect to t? Okay, that's what we want to do next. But once you have that, if you want to do three-dimensional motion, let's say you have something like this, and the trajectory can actually go up and down and forward and back into the ring or outside the board, you can simply apply the idea you have here directly to here, because all you need to do is just add another z. Okay, then you will be able to find any kind of velocities, which is the derivative or acceleration or force in 3 dimension. That is super beautiful. If you think about it, you don't even know how to define the derivative in 3 dimension.